Okay, welcome to video part one of our lecture series from Friday, April 7th, where we are going to practice now what we know about pH and pOH calculations to see if we can't determine the pH of a particular solution. So in this example, we are asked to determine the pH of a 1.25 times 10 to the negative 4 molar solution of barium hydroxide. So we have a couple of pieces of information here. And in order to tackle this problem, I think I'm going to start by just writing out what we know about things like pH and also what we know about what barium hydroxide looks in solution, and then also what that means for our concentration. So like these are kind of the main pieces of information that are given in this problem. So to start, to determine the pH of this solution, I'm going to write the equation that pH is equal to the negative log base 10 of concentration H plus. Okay, so that is one thing I know about pH. And another thing I know about pH is I know that the sum of pH and pOH is equal to 14. Now, I don't yet know if I need to use this particular piece of information about pH, right? Starting with the definition is always like kind of the best place to start, but I'm going to put it up here anyway, just to see if it maybe becomes useful in a moment. Okay, let's next think about what our solution contains. So we've got barium hydroxide. So when we dissolve barium hydroxide, we would likely predict that this would be a basic solution that forms as a result, because according to our Arrhenius definition, we have hydroxide particles in this compound, and this compound is soluble. So when it dissociates into solution, I generate the barium 2 plus ion, and then two of my hydroxide anions. So I've got base particles, so I know that in my solution, if I were to dissolve 1 mole of barium hydroxide compound, that is the solute, then I would expect for there to be two of our hydroxide or base particles generated based on the chemical formula of what barium hydroxide is, right? That's BaOH2. So if I dissolve 1 mole of BaOH2, I generate 2 moles of hydroxide anion in solution. So I'm going to show, instead of 1 mole, I'm going to show 1 molecule because I don't want to draw out 6.022 times 10 to the 23 little ion representations. So I've got here barium 2 plus, and then two of my hydroxide ions. Looking at our solution from this perspective, we again justify to ourselves that this means that we are a basic solution. Because we've got these hydroxide particles in solution. Now, why was this an important thing to look at? Let's go back to what the question is asking. We are asked to determine the pH of this solution. And if I look at my definition of pH, I see that the pH, or measure of acidity of a solution, is the negative log base 10 of my concentration of acid particles, or H plus in solution. So if I look at this solution, my barium hydroxide solution, since we're a basic solution, I don't have H plus, but rather I have hydroxide ions. So I can't directly calculate pH because I don't have my concentration H plus, because in the solution there are no H plus ions. So it turns out that this relationship between pH and pOH was useful, because if I rearrange this expression to get pOH and pH related, I see that pH is equal to 14 minus pOH, where pOH is helpful because pOH is the expression that does depend on the concentration hydroxide. So pOH, by definition, is the negative log of my concentration of base particles, hydroxide ions. This is what we have in solution, and we should be able to figure out its concentration. So we're gonna have to solve for pH indirectly by first solving for pOH. So this means we need to figure out the concentration of hydroxide particles in solution. This is why this kind of solution perspective analysis was useful, because if we notice the ratio of barium hydroxide to hydroxide ions is 1 to 2, meaning that the concentration of my hydroxide ions is twice that of my concentration barium hydroxide. So let's figure this out. Let's see if we can't determine what this concentration is. So looking back at my problem, I know that my concentration of barium hydroxide was given to be 1.25 times 10 to the negative 4 molar. And as we said down here from our analysis of the dissociation of barium hydroxide in solution, we know that our hydroxide concentration is twice that of the concentration of barium hydroxide. So this is twice of 1.25 times 10 to the negative 4 molar, or 2.50 times 10 to the negative 4 molar. So because we have a concentration of hydroxide of 2.5 times 10 to the negative 4 molar, meaning it's something that's known, we can now take this and plug this in to our pOH equation. So pOH is the negative log base 10 of concentration of hydroxide in molarity. And we have that concentration. That is what we just solved for here. This becomes the negative log base 10 of 2.50 times 10 to the negative 4 molar. Now, sig figs with pH and pOH is a little weird. I am not going to teach you guys the pH rules, or sorry, the sig fig rules for logs. So in this class, I'm okay with you reporting pHs and POHs, so only 3 sig figs. That's all right. If you want to discuss the way that we could determine uncertainty after undergoing a logarithmic kind of function, we can, but that's not something I want you to really care about at this point in Chem 210 at least. So when I plug this into my calculator, I take the log base 10 of 2.5 times 10 to the negative 4. So I would actually write out in my calculator 2.5 times 10 to the negative 4, enter, and then take log base 10 of that, enter, and then multiply by negative 1, enter. So when I do this, I get a POH of 3.60 to 3 sig figs. Okay. Now let's make sure that we have done something right here. So remember, low POHs imply that we have basic solutions. It's the opposite of the pH scale. So we would then expect a high pH. So let's go back and use our equation that says that pH is 14 minus POH. So pH is equal to 14 minus my 3.60 POH, meaning that the pH of my solution of barium hydroxide is, let's see here, that is 10.4. And as we expected, a high pH, we see a high pH. So we can say that this is a reasonable answer. So we now have the pH of the solution despite it being basic because we know the interrelationship between pH and POH. So let's kind of recap what we did here. Things to pay attention to. 1, pay attention to whether or not you are a base or an acid that is being put into solution, because that will determine whether or not you need to calculate or are able to calculate directly a POH or a pH. Another thing to pay attention to is the concentration, not just of your solute, but your relative concentration of either basic particles or acidic particles. So you do need to consider your dissociation equations, just like we did when looking at our electrolytes lab. And then you need to ensure that you recall this relationship between pH and POH in case you are asked for the opposite of what you're able to directly calculate based on what kind of solution you have. All right, so this is how we calculate pH or POH in solution. We've done both here. We just got to pay attention to what's going on in solution. So anytime I say aqueous chemistry is all about thinking about what's happening in the beaker, I literally mean try to put yourself in the perspective of what's in the beaker, what ions are present and in what proportion. That's going to really help you out when you're doing any kind of pH, POH, concentration, and even, as we're going to see next, stoichiometric type calculations. So that was our warm-up for the day. Let's move on into our next topic, which is the idea of stoichiometry, which we have called kind of lightly in the past mole counting. So see you in part 2